Lecture 7 covers section 3.3. At the end of today's lecture, you should be able to construct a force couple equivalence. That is, you should be able to express a moment as a couple plus a resultant, and you should be able to express that couple and a resultant as a resultant acting on some distance from our axis of rotation. To begin, let us recall that if we have a force, F, acting on our moment arm, R, that we are going to generate a moment of force about point O. This is shown in the figure below. Now, it is our goal of this lecture to re-express this moment in terms of a couple and a resultant force. Recall a moment has a tendency to rotate and translate, and recall a couple only has a tendency to rotate, and then our resultant force is going to be applied in such a manner that it then yields our tendency to translate. Now, to achieve this goal, we are going to apply two equal in magnitude and opposite direction forces F, known as fictitious forces, which are going to be parallel to and in plane with their original force. These two forces are going to be applied about point O, as shown in the figure below. We have F acting up and to the right and down and to the left about point O. Now, since these two forces are equal in magnitude and opposite direction, they will cancel out each other's tendency to cause translation. Additionally, since these forces are acting about point O, there's going to be no new tendency for rotation. Now we see that if we take the force on the bottom left and our original force F that was generating our moment, that these two forces create a couple. Now our couple is a free vector and we can move it anywhere on our body. So, as shown in the figure to the right, we will take these two forces and the resultant couple and apply it about our part center O. Now, the last remaining force, the red F, is going to be acting about our part center, i.e. our axis of rotation. And this force is only going to create a tendency to translate. Thus, we can re-express our moment, which was a force acting on a moment arm, as a couple plus a resultant. In this situation, our resultant is just F, which is acting about point O. We want to further reduce this. And since we have a couple and a resultant lying in the same plane, we should be able to re-express this in a moment. That is, we should be able to take F and translate it into a parallel position, some distance d away from point O, which is going to cause a tendency to rotate and translate as well. Thus, the sole effect of combining this couple with a force is to move the line of action of our force into a parallel position. Now, we can say two different force systems are equivalent if they are going to produce the same external effect on our body of interest. That is, the figure on the left shows our original moment of force. The figure in the middle shows our couple and our resultant. And lastly, our figure on the right shows our force applied at some distance d away from our part center. To do this, we have to look at a generalized situation. Say we have n coplanar forces, F1, F2, all the way up to Fn, acting on moment arms R1, R2, all the way up to Rn. Now, to determine the net effect on our body, we need to determine our total tendency to translate. That is, we need our resultant force by summing up all our individual forces on our system, and we need our total tendency to rotate. That is, we need to take the sum of all our moments about point O. Now, we know our resultant is equal to the sum of our forces in the x direction plus the sum of our forces in the y direction, and the magnitude of our resultant is the square root of the sum of the squares. That's rather simple. Now we have to determine our net tendency to rotate. That is, we need our moment about point O due to our resultant force. Now, if we recall from slide 7, we need to do this such that we can determine d, the distance away from our part center, as to where we will apply our resultant force. To determine the line of action of our resultant force with respect to our part center, we are going to go back to the principle of moments. That is, our moment about point O due to our resultant is going to be equal to d cross r. That is, d is our distance away from our part center cross our resultant force, and this is going to be equal to the sum from I is equal to 1 to n of r sub I cross f sub I. That is, our total moments on our system due to each of our individual forces acting on our individual moment arms. The magnitude of our moments must be the same in our previous expression, and thus we can move r into a parallel position until we find the correct location that yields the same magnitude of our moment. That is, in a scalar form, we can solve for d, the distance from our part center to the line of action of r, that is going to give us this magnitude of our moment. That is, we can say d is equal to our moment about our part center O due to our resultant force per our resultant force. To determine the line of action of r, we can find the intercept with respect to the x-axis. In the figure to our left, we have our couple and a resultant, and we will decompose our resultant to our x and y components. Now in the figure in the middle, we will translate r into a new parallel position. And in doing such, we are going to move along the x-axis. And in doing such, we see r sub y is the only component of our force that is going to contribute to our moment. R sub x is in line with our part center O. Therefore, we can find our distance x from our part center as the magnitude of our moment due to our resultant force per r sub y. Alternatively, we can solve for our y location. That is, if we look to the figure to the right, we will translate r downward along our y-axis, and we see r sub x is acting some distance y about point O, and this will cause our rotation within our system. R sub y is not going to contribute to our moment since it's in line with our axis of rotation. Thus, we could alternatively solve for our y distance as the magnitude of our moment about point O due to a resultant per r sub x. Now note, we can solve for one or the other. We cannot specify both simultaneously.